Welcome to today's podcast about Raman Spectroscopy, brought to you by Spectroscopy Magazine and tec5usa. Today we have the Systems Product Manager from tec5usa to tell us a little about some of the challenges of incorporating Raman instrumentation into process control. tec5usa offers high-quality products for UV Vis, NIR, and Raman spectroscopy. For more information, please visit them on the web at www.tec5usa.com. And now, here's your host for this podcast, Fred Gebhardt.
Hello, everyone. This is Fred Gebhardt, contributing editor of Spectroscopy Magazine, and I'm here today with Stacy Carrier, Systems Product Manager at tec5usa, Inc. Today, we're going to be discussing Raman spectroscopy and process control. Thank you for being here today, Dr. Carrier.
Thank you.
To get us started, there's been increasing interest in Raman spectroscopy in the last year or so. What is Raman spectroscopy, and why are so many people getting so interested?
So Raman spectroscopy is a vibrational spectroscopy. It means that you can actually measure the vibrations of the atoms within the molecules. And one of the great things about a vibrational spectroscopy is that it is very selective. Every molecule has a unique vibrational signature because every molecule is made up of different atoms, and when those atoms vibrate, they give off very different and very characteristic frequencies that allow you to determine not only what you have, but it also can tell you how much of a molecule you have in your sample, which makes this very complementary to the information that one will gain through mid-IR spectroscopy, like mid-IR spectroscopy and UV Vis spectroscopy. It is also a non-destructive technique, which means you can sit there, you can pipette a small sample out of your reaction chamber, put it into a cuvette, and take a spectrum before you can dump it back into your reaction vessel, which in some ways it's very necessary because certain chemicals can be very expensive and you don't want to waste those. Now, because this is a vibrational spectroscopy and it has a unique vibrational signature, it means that the number of applications is huge. It's ginormous. And, there's just a few. First of all, like in semicon, Raman can actually be used to measure the crystallinity of silicon or other semiconductor materials, but you can also tell the amount of stress and strain in these crystals, which becomes very important because we all want really nice TVs to look at. So the amount of stress and strain and the amount of crystallinity become very important factors. Now, most people are looking at things like chemical manufacturing or pharma because, again, this is a very unique way to identify and quantify exactly what you have. So people are looking towards Raman because it has some advantages and disadvantages over mid-IR spectroscopy.
Okay. One of the things we've seen is that FTIR, near-IR, UV Vis spectroscopic techniques have become very widely used in both research and industry. Why hasn't Raman spectroscopy gained as much traction in industrial processes?
There are several issues that I can see of why Raman spectroscopy hasn't gained a lot of notice within the world of industry. The first issue is that Raman spectroscopy requires a single wavelength light source, and usually these light sources, in order to have the amount of power necessary for Raman, is that they're lasers, and lasers can be dangerous. So in order to put this into process control, you have to have extra safety precautions. You also need to make sure that your workers and your operators know how to safely operate a laser and not injure themselves by potentially blinding themselves. So the other reason a problem with lasers is that they're expensive. After playing with lasers in university, I know how expensive some lasers can be. So in order to get a good, stable laser, it's going to cost a lot of money. Okay. However, the main reason that I see why Raman spectroscopy isn't huge in industry is that it is a very weak process. Since Raman is based on inelastic scattering, and unfortunately what happens is that only 0.001% of the light that hits a molecule is inelastically scattered, which means that you have a very, very weak process, and you have to figure out ways to either cut down on background signal, or you have to figure out ways how to enhance the signal. There are numerous methods out there that are looking into enhancing the signal, and we're talking about surface-enhanced Raman, tip-enhanced Raman, anti-coherent, anti-Stokes Raman scattering. All of these techniques are designed to enhance the Raman signal, but when you're looking at process control, you don't always have the time to wait to enhance the signal as much as necessary. And finally, in less importance, is that using the single wavelength light source, you can also create a fluorescence background. And since you're dealing with a really weak signal, having this large fluorescence background, a lot of times it tends to overwhelm the Raman signal. And so people have been working to figure out ways to cut down on the fluorescence or try to subtract it out. You can do that fairly easily by moving to higher wavelengths. The excitation wavelength actually plays a role in how much fluorescence is produced. And the other problem with this is that you can continue to go to higher wavelengths, but eventually you're going to run into making a laser at a high enough wavelength. Common ones are 785, 800, 1064 lasers are very common, but once you get above 1,000 nanometers, you have to move to a much more expensive, less stable technology of lead selenide, InGas, things like that, where you're moving deeper into the near-IR spectrum. So in order to bring costs down, many people choose to work with 633, 785 to work with the less expensive, more established silicon technology.
Okay. With all of these hurdles, what are some of the advantages of Raman technology?
Some of the advantages of Raman spectroscopy, I'm actually going to compare this in 2 or 3 lumps because to make it a little bit simpler. First of all, to compare it to UV vis spectroscopy, you're dealing with a vibrational spectroscopy versus an electronic structure spectroscopy, which means that you tend to have a lot more structure in the vibrational spectroscopies. It makes it so you have a peak, in 3 or 4 different places rather than just one large 400 nanometer bump. Now, the very large bumps can be very useful, but the problem becomes is that when you have a large mixture of numerous compounds, you can get these massive blobs, for lack of a better term. They can start overlapping each other, and they're shifted only by, a couple nanometers, and it becomes very difficult to distinguish between the features being given by various compounds. Now, for the vibrational spectroscopies, Raman is most analogous, it's most complementary to mid-IR spectroscopy. Now, except for Raman, it's actually easier to use and process for some reasons. First of all, mid-IR, a lot of times the instrumentation has moving parts in order to get the resolution necessary and the wavelength range necessary. It has moving parts, which is something in process control people want to avoid, simply because a moving part means that someday it will break. Some other reasons that mid-IR is difficult to use in process control is that a lot of the materials that are necessary, the transparent materials needed to take spectra they love water. They'll dissolve in water over time. So you're looking at calcium fluoride, barium fluoride, sodium chloride, these types of windows. And over time, they're actually going to start absorbing water and messing with your signal, which is something you kind of want to avoid. So with Raman spectroscopy, you can actually start working in the visible. You can take the entire spectrum in one go without any moving parts, and you can move to nice optical materials like quartz or sapphire, both of which are very sturdy to air. But one of the main advantages there are a couple main advantages of Raman spectroscopy outside of what I've just listed, is that Raman spectroscopy is unaffected by polar bonds. So the carbonyls that you get in sugars, the OHs that you get in water, any of the halogen molecules, Raman's not very sensitive to these, which means one of the most ubiquitous compounds that we all love here on Earth is water. And mid-IR, both mid-IR and near-IR have huge water signals that kind of occasionally drown out like any other signals that you have. Raman spectroscopy ignores this. It has very, very minimal sensitivity to water. So all of a sudden you're working in an aqueous solution, you no longer have to subtract out that water signal. So another advantage of Raman is that it's actually capable of detecting nitrogen and oxygen, so N2 and O2. In the UV, you have to go below 180 nanometers, which, unless you're going into vacuum UV, it's very difficult to monitor this in the UV. And these molecules are just not detectable via infrared spectroscopy, which means that if you're using UV vis and mid-IR, a lot of times in process control, they'll have to use a different technique to monitor nitrogen and oxygen. And with Raman, you get it all in one shot.
Okay. How does your Raman system overcome some of the common challenges that are faced by users?
So tec5usa focuses mostly on process control instruments. We prefer to have our instruments performing where they were meant to perform, which is inline analysis. It means that an instrument, in order to be put into process control, needs to be two things. It needs to be fast, and it needs to be reliable. You have reactions that are proceeding, you're shooting things down pipes at a very, very fast rate. You need to be able to take data very, very quickly. And then you need to know that the data you collected is reliable. You need to know that life is good. So there are not many companies that have Raman systems for process control. Most people who are using Raman have actually taken a lab instrument and are using that lab instrument as, not a continual monitoring step, but it's a verification or a recalibration step. So in order to be able to move this into process control and to do it easily, you need to be able to monitor the Raman spectra continuously. Yes, you may be only taking data every minute or every 3 minutes or every hour, but you need to be able to take this continuously. You don't want to have to stop a process every 30 minutes just to take a sample and verify that things are going okay. You want to be able to do this in line. You want to be able to have the software that says, here's your spectrum, let's stop the process if something's going wrong, if the concentrations are off. So one of the things that Tec5 has provided is that our systems have a very stable light source with a very highly sensitive detector with permanent wavelength calibration. It allows the steps needed for recalibration or verification, most companies will do it like once a year regardless, but it means that you don't have to do it between every single data point, which makes it much, much nicer for 24/7 use. The other advantage is that we use fiber optics, so you can put the system several meters away, take an immersion probe, and stick it directly into your pipeline. You can stick it directly into your vat of chemicals. And so the only thing that is really being exposed to your sample is a probe. And then the probe sends the light to our system, and the system, using our software, can literally just take data and communicate with a process control system.
Great. What are some of the future goals of tec5usa with respect to the Raman spectroscopy?
So, as I mentioned before, we currently focus on, or maybe I didn't mention it before, but we currently are focused on UV-Vis and near-IR systems for process control. We have thousands of systems and units within both the U.S. and Europe that are monitoring processes daily, 24/7, in semicon, process chemical, agriculture, thin films, and a whole bunch of other applications. For Raman, what we are trying to do is we would like to be able to establish our Raman system within the industries to show that there is a system that can monitor their processes at 24/7 for several months, and give a viable alternative to near-IR spectroscopy.
All right. Well, thank you very much for that overview, Dr. Carrier. We appreciate you being here today. This has been Fred Gebhardt, contributing editor at Spectroscopy. Thanks to all for listening, and goodbye.
Thank you for listening to today's podcast about Raman Spectroscopy, brought to you by tec5usa. For more information, please visit them on the web at www.tec5usa.com.